as I just mentioned, this here, okay, D also can be written like, because if you have this, to again, because you have P, you have P, right? So, and there's epsilon 0 and epsilon. So this D displacement can be written like E plus P, right? This is again. There is an E. Right? So I want to prove how this term is equal to this term. Right? It's equal to this term. So you can write like this is epsilon 0 E and epsilon 0 E plus chi E and Z. Okay. So this is E chi. Okay. So this term we call the chi E is susceptibility. Okay, susceptibility. Susceptibility is something like also, I would say, it's how the dielectrical molecule can be switched, okay, can be switched by the external field. How stress the dielectrical materials can be pulled by the external electrical field. Something like I ask you guys, for example, give me a crab. Give me a crab. Give me a crab, please. Okay, so your susceptibility will be more higher, but someone's susceptibility is low. Do you understand what I mean? So similar to this, because I have announced something, right? So I announced, give me a crab, just like I apply electrical field, right? So some molecule switch strongly. Some molecule is hard to switch, right? It's hard to switch. For example, the dielectrical materials like the insulator, because their dielectric constant is quite strong, so the susceptibility is very high. So unless you apply the stronger electrical field, and they can switch. If there is a very weak electrical field, it's hard to switch. So we call this as a susceptibility. In the Mandarin, it's called as 感化率, 感化. Right? So this is also something relative to dielectric. Okay. So and then we can rewrite this epsilon 0, 1 plus E, right? Right? So this will be equal to epsilon 0, and this is epsilon. This term, right? Someone also call this is relative epsilon. Okay? So this is similar to here. E. Dielectric, right? E. So if we read some textbook, they call the epsilon is relative. Relative. right? So this is a dielectric displacement. All right. So under this situation, you have the surface charge density. Okay. You have the surface charge density. So this is just a new slide I will send after the review. Okay, this is I already write it here. So this is under the vacuum, right? Under the vacuum. Epsilon E0 is intrinsic electrical field without heating. Okay? And then if you place the materials to here, right, the dielectric material, then you will induce the polarization, right? This is the polarization. So this polarization also has an internal electrical field, which is opposite to the external electrical field, right? External electrical field. So this external electrical field will be subtract by internal electrical field. So therefore, overall external field will be become to this. Okay. And then remember about here. Be aware about here. This has a charge, right? Induced charge. Okay. This is induced charge. So I would say this is C is induced surface charge, and their electrical field internet induced electrical surface charge. And D is the remaining magnitude of the electrical field. This is the remaining remnant, okay, resultant, also called resultant. That means that because the external field has been weakened, okay, has been weakened. So K here is a dielectric, okay, dielectric constant. Okay, sorry if there is a different sign. Okay, you can revise to epsilon as well. Okay. So this is similar on a previous point. Okay, our previous point. Okay, dielectric is placed to the plate. Okay. So this is the surface charge. Okay, surface charge density. Okay. So if we finish about this chapter and then as this slide, I will start to talk about the slide of the piezoelectrical materials. Okay, the slide of piezoelectrical materials. So piezoelectrical materials possess the property, okay, that can generate the charge on the surface electron. Okay, on the surface electron. So under deformation, okay, under deformation, if you can look at about here, because inside create a polarization, as I mentioned, right? Inside create a polarization. So therefore, this is a positive and negative, right? Which will generate the surface charge. So this surface charge is also called dielectric displacement, right? Dielectric displacement. So this dielectric displacement D is equal to Q and A. Q is the charge, right? A is the surface, right? Is the surface. Okay? So for the dielectric displacement, for the piezoelectric materials, actually you have two kinds of the piezoelectric phenomena. One is converse, okay, converse piezoelectric effect, which means if you apply, okay, you apply the stress, okay, apply electrical field, and then the dimension will change. This is the converse, okay. In contrast, if you apply a force, for example, this button side, we apply the force because this force will generate polarization, and this polarization will induce the charge, right? So create electricity, okay? Because this is positive, this is negative, right? So you can measure the output voltage as long as you pulling, you making the stress to these materials. Okay, so this is a direct, we call it direct piezoelectrical effect. In contrast, if you apply the electricity, right, you apply the electricity, because inside of the polarization will be changed, okay? So therefore, which force the dimension change, okay, force the dimension change. So therefore, this is become converse piezoelectrical effect. Later on, I will further to explain about this term, okay, further to explain. So accordingly, you have the direct and converse piezoelectrical effect, okay. This is a reciprocal relationship of the piezoelectrical materials. Okay. So this is what polarization have in the piezoelectrical materials. Because we talk about inside polarization in general, right? If you look at about direct, okay, piezoelectrical coefficient, piezoelectrical effect, you can see, for example, there is a ferroelectrical materials, okay? Now I further introduce about ferroelectrical and piezoelectrical. So you might elucidate, like, Professor, what is the difference of the piezo and the ferro? This is piezoelectric, right? And this is ferroelectric. Okay? So for example, piezoelectric, there's some representative materials like tin oxide, like indium nitride, like gallium nitride. Most of them is two components, consist of two components. And the ferroelectric materials of most of them NDO3. Postcard. Okay, like a PZT, PDZR, TiO3, like a BA, TiO3, like a NaMbO3. Okay? Those of them are similar to this structure. Okay? Just like a horse. Horse has a white horse and a black horse, right? So horse is the big field, right? But white horse is only a small field, right? Horse, you know? Is that okay? Just like you know the horse, right? 马 right? 白马跟马都是马嘛，对不对？ Horse, you have a white horse, you have a black horse. Those are different, right? Color, but those are horse, right? So ferroelectric only focus on the small field, okay? Ferroelectric focus on the small field, but piezoelectric is a big field. But ferroelectric, if you let the material has a ferroelectric property, that has a polarization, okay? And piezoelectric material also have the polarization, okay? But you may be curious, and what is the difference? What is the difference? Piezoelectric materials, the polarization cannot be switched. But ferroelectric, the polarization can be switched, okay? Look here. If you look at about the PZT, now there's a TC, okay? TC is a curious temperature. TC here is a TC. You can add the TC. Curious temperature is a critical temperature called Curie temperature. exist about which ferroelectric effect are destroyed and the material become ferroelectric. Is that okay? So that means if the temperature above Tc, if the temperature is above Tc, and then there is no polarization. Because if you look about these materials, you have the titanium, zirconium, lead, and oxygen ion, right? So the titanium and zirconium is right here, right? If the temperature is higher than Tc, and then this titanium or zirconium will position it at the center point. So there is no polarization. Okay? But if the T is below 2 Tc, and then this titanium or zirconium ion will shift to this position. Or you may ask me, where is shifted to button side? Yeah, of course, if you look at all this side, yeah, there will be button side. That means that you will shift, right? So if you look at all this, the distance from here to here and from here to here will be non-equal, right? So therefore, the charge will be difference, right? So the charge will be difference, that means that there's an internal polarization around this direction. Is that okay? Because this is positive, right? This is positive. Okay? So we call this as internal polarization. Okay? But if you use the electrical field to represent this phenomenon, electrical field will become this way, right? Right? Is that okay? Electrical field will be down this way. So inside has a spontaneously. Spontaneous, that means 自发性 polarization, right? Spontaneous. That because once the material has been grown, already exists the polarization. Alright? So you may ask me, Professor, what is the Tc? What is the exactly temperature of the Tc? I would say it depends on the materials. For example, BaTiO3, it will be about 100 degrees. And some of the materials, the Qs temperature even more higher, right? So the Qs temperature for different material has a different Qs temperature, right? Some of the material will be high, some material will be low, right? So it depends on the materials. So that's why, if you look at about the Qs temperature, you can see if the Qs temperature is 100 degrees, for example, and then if you increase these materials to the 100 degrees, there's no polarization because the deviation, titanium zirconium deviation will shift to the center position. So the distance, bottom side and the top side will be equal. So no polarization. And when once the temperature below the Qs temperature, and then this titanium zirconium shifted to the center position, okay, away from the center position. So create a polarization. Okay? Is that okay? So all of them, ABATiO3, PBTI, ZiO3 has the same situation, looks like that. Okay? But for the zinc oxide has also spontaneous polarization because this zinc has a slightly deviation. Okay, align the direction. But what is the major difference for these materials and zinc oxide? If I apply the electrical field externally. Let's look about this unit cell. This unit cell okay, this unit cell. You have a tissue. You have a tissue. And then you have the titanium. Shift to this position, right? So we know there is a poly, right? But now this atom is right this way, right? If I apply, this is the titanium or zirconium, right? If I apply an electrical field, external electrical field to this direction. So what about the unit cell? Polarization, will that be changed? This is a, be aware, this is a, this is spontaneous polarization. That means materials being grown, polarization already exists there. Okay? But this is a ferroelectric materials, T below Tc, ferroelectric. So if you learn about this electrical field applied to the opposite of the polarization, you could see this is a titanium positive ion or zirconium positive ion will be switched. Okay? This dipole will be switched to opposite direction. Which means this will be pulled down to here. Right? Because the external electrical field being switched. So, this is a similar. This is similar to that. If you have the materials domain, for example, the materials domain looks like that. P, 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 for example, you have this P, right? And then if I apply external field, it will become you will be switched to this P, right? Because under this electrical field. This is for the ferroelectrical materials MeO3. Okay, only for ferroelectrical property. Okay? But for piezoelectrical materials, okay, yin oxide, indium nitride, gallium nitride, there's no way to poly. Is that okay? You cannot apply electrical field to switch the zinc deviation. No. Okay, impossible. Okay, so only the ferroelectrical has such advantage that we can flexible to tuning the electric field, so therefore the dipole moment can be switched under the electric field, under you apply electric field. So if you grow like the zinc oxide, and then there's a random depolarization, and you ask me whether it's possible to apply electric field to align them, is impossible, okay? Because the spontaneously polarization in growth already exists. So it is not possible to switch their domain. Okay, their domain. Okay? Okay, so certain materials such as barium, titanium, BaTiO3 is BaTiO, resist spontaneous polarization without presence of the external field. Because this material has electrical dipole, their dielectric constant may be ordered, okay, high, okay, large than those non-polar dielectric. So-called, that's why BaTiO3 has a higher, okay, order higher. Ferroelectrical is the materials in which this dipole can be reoriented using external electric field, right? So that means if you apply external electric field, the orientation can be reoriented to any direction that align to the external field, okay? Based on the external field. So this is that's why you usually you could observe this is what we call the PE curve. Okay, PE curve. Polarization versus the electrical field. Okay, polarization versus the electrical field. The polarization versus the electrical field looks like that. There's a P curve. This is polarization and electric field. So at the initial, okay, at the initial, the poly may be random. Okay, and once we apply electric field, you could see this will be looks like that. Pauling will be increased to here. So the microstructure you could see Pauling can be switched to this domain because once you apply to the electrical field to here, okay, and once the electrical field release, change to here. So this is PR. PR that means that remnant. Remnant polarization. PR. Remaining, okay, which which is a remaining polarization. So this remaining polarization, it will look like the polarization will slightly shift, but still can maintain the same direction. But once you apply the negative bias, negative electrical field, you will switch to here. Okay, so to here, you will see this polarization will be always follow the opposite direction because you apply a negative bias, right? You apply a negative bias. And then under here, you could see, oh, the bias will be random. And mostly they trend to this direction. Okay? Finally, you apply, okay, a positive bias, you will trend to here. Okay? So this is a PR, negative PR. You still could see the polarization slightly change. Slightly change. So to tell about how the ferroelectric property has a high I would say the high ferroelectric of ferroelectric property or not, it depends on the PR and the electrical field in the product. If the curve looks like that, okay, if you have the A curve, for example, this is the B curve, and there's a C curve. So C curve. This is C. Green is the B curve. You have these three curves. That would say A, for the A curve, you could see you just need to apply a small electric field, and you can increase the polarization, right? Right away. But for the CV curve, you have to apply a large electric field. So therefore, you can get the PR right here. But for the C curve, you still have to apply, for example, more exaggerated will be, looks like that. Sorry, let me change. It means this curve it looks like you have to apply a large electrical field. So therefore you can get the polarization. But this polarization is still lower than A and B curve, right? Under such large electrical field. Right? So there is a poor PR, right? Poor PR for the C curve. Right? Okay? Is that okay? So the curve determines about how large PR that we can achieve under the external electrical field. The smaller the electrical field being applied, the higher the PR you obtain. That means the ferroelectrical property will be better. Okay, will be better. But if we apply the large electrical field, okay, and then you just get the small electrical PR, right here, small electrical PR. This is PRC for C curve, right? This is PR for A curve, right? This is PR for B curve. This is PR for A curve. Okay? Okay? So PR A larger than PR B larger than PR C. Okay? Okay. So polarization is depends on what electrical field we apply. Okay, so you have, for example, titanium zirconium is right here. So you have the difference domain. Okay, this is a schematic diagram to represent the spontaneous alignment. Okay, alignment of the electrical dipole. So within the domain, okay. This is a random domain, right? But after we apply the huge electrical field, this domain can be switched. Okay, this domain can be switched. So this is a definition, okay? Because it's a definition for the dielectric piezoelectric coefficient, okay, effect. Stress is used to generate the voltage, okay? And then converse electrical effect, piezoelectric effect is a applied electrical field produce a change in the dimension in the ferroelectrical materials. Okay? So which means electrical field applied to the whatever for the materials of the piezoelectrical or ferroelectrical, they will change the dimension. Okay, they will change the dimension. And this is a converse. Okay. So that means so-called once we apply electrical field, and the dimension changes, we call this as a converse. And once we apply the stress, or the strength, okay, produce the electricity, and this is the direct piezoelectric coefficient. Is that okay? Okay? Okay. And this is also a definition of the TC we already mentioned. Okay, we already mentioned that Cure's point is the temperature at which ferromagnetic, whatever for the ferromagnetic, okay, or electrical. Okay, here is a magnetic. Okay, so if you mention about the magnetic, okay, magnetic, which is similar, okay, whatever for the electricity or the magnetic also have the same, okay, have the same Curie temperature. So you have the ferroelectric, magnetic or anti-ferromagnetic materials. They become the ferromagnetic. Okay, on heating, the effect is reverse. Okay, so the magnet will lose its magnetism. Okay, so if you heat about the Curie temperature, so this is similar to the magnetic materials. Now we didn't talk about magnetic materials, but all the mechanisms are similar. Okay, are similar. So that's why if you have read about the textbook for the magnetism of magnetism materials, they have the similar Curie temperature. And then also, the magnetism will be called N and H loop. Okay, they have the same loop. N is the magnetic being applied. Okay, sorry, it's a I would say the magnetism being induced. Okay, H is how much magnetism field being applied. Okay, that's the difference. Okay, anyway, they have the similar Curie temperature. Okay, Curie temperature. If the Curie temperature lower than if the temperature lower than Curie temperature, and then they spin together. Okay, under the external magnetic field. Okay, if Curie's temperature is higher, okay, if the temperature higher than Curie's temperature, and then the magnetic spin are random, okay, are random. That means they lose the spin moment. Okay, they lose the spin moment because next there is the external magnetic field is applied. Okay, is applied. So for the ferromagnetic or ferroelectrical materials are similar mechanism, similar mechanism, because those of them have the spontaneous polarization. Okay, and then this spontaneous polarization will be lost after the temperature higher Tc. Okay, higher Tc. Do you know about some of there is electrical, I would say, how to say, electrical pole, 电锅啊，电锅的英文怎么讲 ？You know, some of the cooking, there's a cooker. Yes, some of the cooker, yeah, electrical cooker, and if you want to use to heating your rice, and then you can put to a cooker box, right? And then you can apply, you know, yeah. You can apply a switch. So once you apply a switch, you will be because inside is the magnetic materials. Once you apply the switch, and then this switch will be because the magnetic materials will be I would say, how to say that, sucking together, right? And then the temperature will be increased, right? Because inside is a heater, the temperature increased. Once the temperature increased to higher than Tc temperature, and then because the magnetic moment will be loosed, so therefore they release, right? Magnetic will be released, pop. So therefore you finish your cooker, and then you have steam rice, right? You have steam rice. So that's the magnetic materials. Okay, the magnetic materials, because you have for example, you have a steel. This is the steel, and this is the magnetic, and then touch together because it's below 2 Tc, right? So these are the magnetic materials, and they touch together. And then inside is heating. And once the temperature upper Tc, release, pop, right? So the functionality of the electrical cooker is similar to that, like that. Depends on the Tc. So this, what time? Okay, let's take a break.